Welcome to Visual Algebra Lecture 4.1, Homomorphisms. Up until now, when we've said that two groups are isomorphic, it's been assumed that for some choice of generators, they have Cayley graphs of the same structure. Naturally, this definition has shortcomings, especially for large or infinite groups. In this lecture, we will finally formalize this by defining the concept of an isomorphism. An isomorphism is a homomorphism, which is a structure-preserving map between two groups. And an isomorphism is one that is also bijective. We will explore this and what it means through a series of examples, and we will prove some basic properties. Of particular importance will be the distinction between injective homomorphisms, which are called embeddings, and surjective homomorphisms, which are called quotients. We will learn how to identify these types just from the subgroup lattices. Okay, let's get started. Throughout this course, we've said that two groups are isomorphic if for some generating sets they have Cayley graphs with the same structure. This can be formalized by a structure-preserving function between groups called a homomorphism. An isomorphism is simply a bijective homomorphism. What we called a rewiring when constructing semi-direct products back in Chapter 2 is technically an automorphism, that is an isomorphism from a group to itself. The Greek roots homo and morph together mean same shape. The homomorphism phi from a group G to another group H is an embedding if phi is 1 to 1, and this occurs when G is a subgroup of H, and it is a quotient map if phi is onto. In this case, H is a quotient of G. We'll see that even if phi is neither an embedding or a quotient, it can be decomposed as a composition of first an embedding with a quotient. The difference between embeddings and quotient maps can be seen in the subgroup lattice. Here are subgroup lattices of two groups of order 20 that we actually saw back in Chapter 2 when we constructed semi-direct products. Both of these are semi-direct products of C5 and C4. In this first lattice, D5 is a subgroup. You can see that because the subgroup lattice of D5 is sitting at the bottom of the lattice of the big group. In the other lattice, D5 actually arises as a quotient. And we can tell that because you see that lattice sitting at the top. Now the dark versus light gray is just only meant to highlight these substructures. And you should see why D5 is a subgroup over here, because it's in the subgroup lattice, but it should not be obvious at all why the fact that it's sitting at the top of the lattice means it is a subgroup. That's going to be a consequence of the celebrated isomorphism theorems that we'll learn later in this chapter. I like to think of this as the difference between stalagmites and stalactites in a cave. Subgroups are like stalagmites that stick up from the ground, and quotients are stalactites. They hang from the top. Often, we'll see familiar subgroup lattices in the middle of a larger lattice. These are called subquotients. Here's an example. I hope you recognize the subgroup lattice of V4 right here in the middle of the lattice of SL2Z3. So why is this called a subquotient? Well, right here, you might recognize that from Chapter 3. That's the subgroup lattice of A4. So it turns out that this group here, mod C2, is isomorphic to A4, and in this lattice, you can see that V4 is a subgroup. So this is a subgroup of a quotient. On the other hand, if you look at Q8, subgroup lattice is over here, and V4 is at the top of that. So V4 is a quotient of this subgroup. So this is one of the themes, that subgroups of a quotient are going to be the same as quotients of a subgroup when these quotients are defined. Again, this should not be obvious. This follows from the isomorphism theorems that we have not yet proven, but it helps going in to kind of know what the big picture is. The isomorphism theorems, they relate the structure of a group to that of its quotients and subquotients. Here's a bit of notation that I try to mostly avoid, but you might see it elsewhere. So let me point it out now. We say things like Z3 is a subgroup of D3. Before I move on, let me just emphasize that that is technically wrong, because Z3 is the set of 0, 1, and 2, where the operation is addition mod 3, and D3 consists of rotations and reflections, so 1r r squared, f rf r squared f. So technically, this is not even a subset of D3. But it is true that there's a copy of Z3 sitting inside of D3, and that's right here. Now there's this correspondence between these elements like this. So you might see this written sometimes to mean that the structure of Z3 appears inside of D3. This can be formalized by a map phi from Z3 to D3 defined by sending n to r to the n. So it sends 0 to r to the 0, 1 to r to the 1, and 2 to r squared. You can see how a copy of the subgroup embeds into D3. In terms of the subgroup lattice, a copy of the subgroup of Z3 embeds into the subgroup lattice of D3. In general, a homomorphism is a function phi from a group G to another group H with some extra properties. We will use standard function terminology. So in this case, we will call the group G the domain. We will call H the codomain. And the image is what is often called the range, like in a calculus class. So we write that the image of phi is just phi of G, which is the set of elements of the form phi of little g, where little g is in the group itself. Here's a formal definition. A homomorphism is a function phi from a group G to a group H satisfying the following property. Phi of A times B equals phi of A times phi of B for all elements A and B in G. Notice that the operation A times B, that is inside the parentheses here, is in the domain, whereas the operation phi of A times phi of B, that's over here, is in the codomain. And if we don't know what the operation is, we generically assume it is multiplication. In the example that we saw on the last slide, from Z3 to D3, this condition above has to be written as phi of A plus B equals phi of A times phi of B. That's because the binary operation in the domain is not multiplication, but it's addition. Not only is there a bijective correspondence between the elements in Z3 and those in the subgroup generated by R in D3, but the relationship between the corresponding nodes is the same. And that's what I want to convince you of in the next few slides. In particular, not every function between groups is a homomorphism. The condition phi of AB equals phi of A times phi of B means that the map phi preserves the structure of G. And that's key. But it should in no way be obvious right away why that condition preserves structure. And that's what I want to convince you of next. So I claim that this homomorphism condition, phi of AB equals phi of A times phi of B, has visual interpretations both on the level of Cayley graphs and of Cayley tables. Let's start with the Cayley graph one first. And I'm going to let C be the product of A times B. We have to call it something. So that means that there is a path from node A to node C labeled with the element B. And when we apply phi to it, so notice that phi of AB equals phi of C, just by definition of C. But now we have equality of phi of A times phi of B and phi of AB, which means that this element C gets mapped to phi of C, this element A gets mapped to phi of A, and this element B gets mapped to phi of B. In other words, we have a path from node phi of A to node phi of C with label phi of B in the codomain. In terms of Cayley tables, let me erase this a little bit so we can see it. In the domain, well, we have A times B equaling C. And then we apply phi, and this condition just means that phi of A times phi of B equals phi of C. So it's like we just replace the entries in the table with phi to get the table of the codomain. If you found parts of that previous slide to be a bit abstract, then I think a concrete example will help. So consider the function phi that reduces an integer mod 5. So formally, this is a map, I claim it's a homomorphism, from the integers z to the integers mod 5. And it's just defined by extending n to n mod 5. Since the group operation is additive in both the domain and the codomain, the homomorphism property becomes phi of A plus B equals phi of A plus phi of B. In plain English, this just says that one can first add and then reduce the result mod 5, or one can first reduce mod 5 and then add the result mod 5. For example, if I ask you to add 19 plus 8 mod 5, how would you do it? Well, I suspect that some people would take 19 plus 8, which is 27, mod 5, which is 2. And what they're really doing here is they're taking phi of 19 plus 8, which is phi of 27. And remember, we reduce mod 5, so that is just 2. Whereas other people would look at this and say, well, I'm going to first reduce mod 5. 19 mod 5 is 4, and 8 mod 5 is 3, and 4 plus 3 mod 5 is 2. So what they're doing here is they're taking phi of 19 plus phi of 8, which is 4 plus 3, which is 2. So you do this homomorphism property whether you realize it or not. Like when you're telling time, you want to add 10 o'clock plus 11 hours. So 19 plus 8, phi of 19 plus 8 equals phi of 19 plus phi of 8. Here's the interpretation in terms of Cayley graphs. 19 plus 8 equals 27. You apply phi. 4 plus 3 equals 2. And in terms of Cayley tables, 19 plus 8 equals 27. You apply phi. 4 plus 3 equals 2. Here's an important remark. If we know where a homomorphism maps the generators of a group, then we can determine where it maps all elements. For example, if phi is a homomorphism from Z3 to Z6, and it sends 1 to 4, then we can deduce that phi of 2, which is phi of 1 plus 1, which is phi of 1 plus phi of 1, is 4 plus 4, which is 2 mod 6. And similarly, phi of 0, well, what is 0 in Z3? It's just 1 plus 2, that's one way to write it. So it's phi of 1 plus phi of 2, And phi of 1 we assumed was 4. And phi of 2 we just deduced was 2. So 4 plus 2 is 0. So just knowing where the generator got mapped to, the generator of Z3, tells us where all of the other elements get mapped to as well. More generally, suppose that a group G is generated by elements A and B, and phi is a homomorphism from G to H. And we know what phi of A and phi of B are. In this case, we can find the image of any element little g in big G. For example, if little g equals a cubed b squared ab, then phi of g equals phi of a times b, b, a. You just write that as phi of a, phi of a, phi of a, phi of b, etc. Now, a quick caveat. Up here, I assume that all of the exponents were positive. And indeed, if k is a positive integer, then phi of a to the k equals phi of a to the k. But what if the exponent is negative? What do you think phi of a inverse is? Here's a proposition, and it contains two basic facts about homomorphisms that will become second nature to us. Let's see what it says. For any homomorphism phi from G to H, phi of the identity element in G is the identity element in H, and phi of G inverse equals phi of G inverse. In other words, phi sends the identity element in the domain to the identity element in the codomain, and phi sends inverses to inverses. Let's prove these. For the first one, we're going to pick any element G in the domain. Note that phi of G is in the codomain. Okay, now what? Well, phi of G, there's not much we can do, is we can write phi of the identity 1G times G. And well, let's use the homomorphism property, phi of the identity times phi of G. And now look what we have. We have an element, phi of G, that is equal to phi of G times some other element in H. But the only element that when you multiply it by something is that something is the identity. So this must be the identity in H. You see that? And that's what we had to show. That phi of the identity in G is the identity in H. So let's put a check mark there. Now let's do the second part. Once again, we're going to take any element in G and now what? Well, phi of G times phi of G inverse, that's equal to phi of G inverse. And that's equal to phi of the identity in the domain. And we just showed that this is equal to the identity in the codomain. So this is by part 1. So what does this tell us? Well, we have an element, phi of G, in the codomain H. And that element times this other element is the identity. In other words, this other element has to be the inverse of that. So this has to be equal to phi of G inverse. And that's exactly what we wanted to prove, that the inverse of phi of G is phi of G inverse. So let's put a check mark there. So as a corollary, if phi is a homomorphism, then, well, we know that phi of gn equals phi of g to the n for all positive integers n, and n equals 0. But from part 2, now we know that it holds for negative integers as well. So for all n in the set of integers z. And I'll let you check that if this holds. It's not too hard to show that phi of g to the minus 2 equals, well, let me just, phi of g minus 1 times g of minus 1, which is phi of g minus 1 times phi of g minus 1 equals phi of g minus 2. So inductively, we get that phi of g to the minus k equals phi of g to the minus k. So in other words, this property of pulling out exponents doesn't just hold for positive integers like we saw a few slides ago, or actually on the last slide, but it holds for all integers. Let's finish with a word of caution. Just because a homomorphism phi from g to h is determined by the image of the generators of g does not mean that every such image will actually define a homomorphism. For example, let's try to define a homomorphism phi from z3 to z4 by sending 1 to 1. So first of all, this should strike you as a little bit strange because z3, the Cayley graph, is a 3-cycle, and z4, it's a 4-cycle. So there's really no way to wrap this 3-cycle around the 4-cycle. And in particular, there's no way, this is 0, 1, 2, and 0, 1, 2, 3. If you try to send this blue edge to this blue edge here, well then 2 blue edges will get sent to 2 blue edges, and 3 blue edges will get sent to 3 blue edges, but that's a problem because that's sending the identity to something that's not the identity. So let's formalize this algebraically. Phi of 2 will be phi of 1 plus 1, or phi of 1 plus phi of 1, which is 2. But phi of 0 will be phi of 1 plus 1 plus 1, because this is equal to 0 in Z3. And that's phi of 1 plus phi of 1 plus phi of 1, which is 1 plus 1 plus 1, which is 3. But that's not 0 in the codomain. And that's impossible because phi of 0 must be 0, because we just proved that homomorphisms send identity elements to identity elements. Now, that's not to say that there is not a homomorphism between these two groups. We can always define the trivial homomorphism that sends every element in the domain to the identity element in the codomain. But there's just not one that sends the generator 1 in Z3 to the generator 1 in Z4. I'll leave you with an exercise and a sketch about how the proof is supposed to go. This asks you to show that there is no embedding from the finite cyclic group Zn to the infinite cyclic group Z, as long as n is at least 2. Another way of saying that is that any such homomorphism between these groups has to send the generator 1 to the identity element 0. In other words, it's trivial homomorphism. And this should make sense because the finite cyclic group is going to be like an n cycle, something like this, and the infinite cyclic group, Cayley graph, is going to be this infinite line, and there's no way to embed the cycle into this infinite line. But how do you prove that? Well, it's going to be similar to what we did up here. So let's suppose that phi of 1 is some integer k, well then phi of 2 is phi of 1 plus 1. Now let's say where we're going. We want to show that k has to be equal to 0. So phi of 2 is phi of 1 plus 1, which is phi of 1 plus phi of 1, which is k plus k, which is equal to 2k. Then we do this, we keep going. So phi of 3 equals phi of 1 plus 1 plus 1, and etc., and we get 3k. But at some point, we get to n. Remember, in the domain, n is equal to 0. So phi of n is phi of 1 plus 1 plus 1, which is phi of 1 plus phi of 1, n times, which is, this is n times, which is n times k. But phi of n, of course, is phi of 0. And we know that homomorphisms send the identity to the identity. So that this has to be equal to 0. So we have n times k equals 0. N is at least 2. And what that tells us is that k equals 0. So this unknown homomorphism has to send 1 to 0. And I think I'm going to leave it there. It's a good place to stop. Coming up next, we will do a deeper dive into embeddings and quotients. And that will lead us to ways to visualize this in terms of both Cayley graphs and subgroup lattices. And then we will introduce a concept called kernel. This is the subgroup of all elements that get sent to the identity. It's like the group theoretic analog of the null space of a matrix or a linear map. So we will introduce that. We will prove that it is a normal subgroup and some other properties as well. So don't go anywhere. I'll see you then.